In yesterday's guided reading, you read about different sources of nuclear radiation. And so today we are going to talk about some of those sources of radiation. And from today's lesson, we want to be able to describe different types of radiation and the specific types that we want to be familiar with that we refer to as ionizing radiation is alpha radiation, beta radiation, and gamma radiation. So we're going to familiarize ourselves with those three types of radiation and be able to write a nuclear decay equation based on those three different types of radiation. So we're going to talk about like what is radiation, why are some substances radioactive, and what happens to these radioactive substances. So in yesterday's lesson or yesterday's reading, you talked about sources of radiation, like where does radiation come from? And so then you can see here from this chart, there are many different sources of radiation, but most radiation that we're exposed to comes from a substance called radon, which is basically just a rock that's in the Earth's soil that is radioactive and undergoes radioactive decay. And so we are exposed to radon more than any other source of radiation. You can see other things that are listed here, medical x-rays. So if you're having like MRIs done or like CAT scans or those types of things, those are sources of radiation as well. Internal radiation, so our body actually produces radiation from within from many of our food sources. So like potassium is a source of radiation. Terrestrial means from the Earth, cosmic means from outer space. And you can see that there's nuclear medicine, consumer products, things like smoke detectors. Those are sources of radiation. So we're exposed to all this different background radiation. And as long as we keep that radiation at a minimum, it's not harmful, right? So a lot of times when people think about radiation, oh, that's harmful. Yes, high doses of radiation in short amounts of time certainly can be harmful, but there is background radiation that we're exposed to constantly that is just normal and does not really have any adverse effects unless we were overexposed to that radiation, right? And so one example of that is, you know, if you have radon in your basement and you live and stay in your basement and that radon is excessively high, then that's potentially hazardous. And so very often if you're buying a new home, there will be a radon test done in that basement, especially if the basement is like a main living area, to see if the radon levels are too high. And if they are, then there's a unit that they can put in your basement, and it's used to remove the excess radon so that the radon levels are not too high. Well, so then what is radiation? Radiation is when you've got the nucleus of an atom. That's why it's called nuclear radiation. If you've got an atom, like the atoms that we've been talking about, and those atoms break into smaller, those nuclei break into smaller particles or give off energy from a radioactive nucleus. And so when we ask, well, what is radiation? Radiation is either particles or energy emitted from a radioactive nucleus. Before we go on to the next slide, I did want to pause for a second and mention this slideshow as well as the video for this Zoom meeting will be posted in Google Classroom. And so if you need access to that later on, that will be available to you, okay? All right, and so, well, what is a radioactive source? A radioactive source is an unstable nucleus, right? And if you remember from the activity that we did on Wednesday, which nucleus did it say from the activity was radioactive? One of the nuclei out of the four that we were working on, it said one of them was unstable. Can you give me a direct message in the chat if you remember which one was unstable? Okay, so remember there were two isotopes of carbon, right? There was carbon 12, which was stable, and there was carbon 14, which was unstable. Yeah, it's okay. Somebody said that they're sorry that they don't remember. That's okay. Right. And so carbon 12 had six protons and six neutrons, and carbon 14 had six protons and eight neutrons, and as a result was unstable. Right. And so that instability comes from the ratio of the protons to the neutrons. If the ratio to the protons and the neutrons is fairly equal, like relatively equal, then the nucleus is stable. But if there are too many protons, I'm sorry, too many neutrons to the number of protons, then that radius becomes unstable. And then what happens is it splits. And when I say it splits, I don't mean that it's cut in half. I mean that it's broken into two parts, which are not necessarily like half of the particles and half of the particles. And so what happens is something like this. Right. And so this nucleus spits out this particle, and that particle can be made up of various numbers of subatomic particles, which we're going to talk about in a second. And then you've got this nucleus that's left over after the particle has been emitted, right? And so you can see this emitted particle contains two protons and two neutrons. And so then this remaining particle here is the nucleus of the atom after the radiation, after the particle has been emitted. And so as a result, it doesn't have the same number of protons and neutrons. And so the remaining nucleus is actually the nucleus of some other atom after the radiation is given off, right? So it's not still the same element. It's it's a different isotope of a different element after the radiation has been given off. This is what we call the parent nucleus, and this is what we call the daughter nucleus, and this is the nuclear radiation, right? So of course, the daughter comes from the parent, just like in human lineage, right? The daughter comes from the parent after this emitted particle has been given off. All right. And so we call this process radioactive decay, where an unstable nucleus loses energy by giving up some type of radiation. Sometimes that radiation is a particle. Sometimes that radiation is energy. Sometimes it's a combination of a particle and energy. And so there are three different types of ionizing radiation that we want to be familiar with. There's alpha radiation, beta radiation, and gamma radiation. And so then if you look at the diagram, you can see that the alpha radiation is the largest particle, right? It's consisting of two protons and two neutrons. And you can see that from the diagram, it's such a large particle that it won't even pass through a sheet of notebook paper. And so the result of that is it's not really very harmful to us, because we really can't have that break our skin or get into our bodies, unless if we take it in by breathing it in, either through our mouth or our nose. The second type of particle, the beta particle, is a smaller particle, and you can see it can go through a piece of paper, but it can't go through a piece of wood that's probably a couple centimeters thick. And the last type of radiation is gamma radiation, and you can see that that can go through the paper and that can go through the wood, but it would not be able to penetrate through what I think is depicted there as a concrete wall, because gamma radiation is actually not a particle at all. Gamma radiation is simply a form of energy. It's a very high energy form of electromagnetic radiation. And so we want to be familiar with these three types of radiation. Okay, so the first type is alpha radiation. Alpha radiation consists of two protons and two neutrons. So you guys know from our previous lessons, and probably from before, protons are positively charged, neutrons have no charge. And so alpha radiation has an overall charge of +2. The alpha particle is equivalent to the nucleus of the isotope helium-4, right? So helium has an atomic number of 2, means it has 2 protons. And if it's helium-4, that means it's got 2 protons and 2 neutrons. Notice I didn't say that it is an atom of helium-4 because there are no electrons, right? It's just 2 protons and 2 neutrons. So it's equivalent to the nucleus of helium-4. There are 2 symbols that we can use to represent the alpha particle. The first one here, this is the Greek symbol alpha, right? So it looks like a little fish, basically, is what it looks like, or it looks like an A with like fancy writing. And so that's the Greek symbol alpha. And then the second one here, this is the symbol for isotope notation of helium, right? So 4 represents the total number of particles from the nucleus, 2 protons and 2 neutrons. And then 2 represents the atomic number, just the 2 protons. And so the first type of radiation we want to be familiar with is alpha radiation. And so now what we're going to do is an example of what we call an alpha decay equation. Okay, so this ugly rock right here is radium. Radium is located in the soil, in the ground. And it is radioactive, and it gives off an alpha particle. It undergoes alpha radiation. How do I know that? Because anytime I give you a radiation equation, it's going to tell you what type of radiation question. It's going to tell you what type of radiation is given off, right? So here it says specifically that it is alpha radiation. Okay, and so if it is alpha radiation, what we want to do here is we want to be able to describe the particle that's given off, and we want to be able to describe the remaining daughter nucleus. And so we're going to go over how to do that right now. So the first thing that we need to do is we need to represent the alpha particle. And so to represent the alpha particle, we know that there are 2 symbols that we can use. The one that I like best is this one. And the reason why I like that one best is because it's more descriptive in what happens to the nucleus and helps us understand the daughter nucleus better. Can you use the other symbol? You can, but it's not as descriptive. So this is your alpha particle. Okay, so then what is remaining after this nucleus loses those particles from the nucleus, right? So you can see that the mass number of this isotope is 226. Well, if we lose 4 particles from that mass number, 2 protons and 2 neutrons, what's the new mass number going to be? What's the new mass number going to be? If we have 226 protons and neutrons to begin with, and we lose 4 of those, what's the new mass number? Thank you, thank you, thank you. Thank you, thank you. Yep, it is 222. Okay, so then the next thing that I want to look at here is the number of protons, the atomic number. So if I look here, I had 88 protons, but I am losing 2 of those. And so how many protons will remain? Thank you. Thank you, thank you. Thank you. Right, 86. Okay, so then if you look at this mathematically, it should make sense to you. What it says right now is 88 equals 2 plus 86, which is true. Up top it says 226 equals 4 plus 222, which is true. And so now here's the last question. If I had 88 protons and the element was radium, and now I have 86 protons, is the element still radium? Yes or no? Is the element still radium? Thank you. Thank you so much. I appreciate your participation. Right, so remember, the number of protons tells us what element we have. And so the only element that has 88 protons is radium. Radium does not have 86 protons. And so to figure out what element this daughter nucleus is, we have to go to the periodic table. And so you'll see in today's assignment, I have included a copy of the periodic table so that we go to the periodic table, and then we're going to find element 86, which is right down here in the corner, right? You can see the atomic number is 86. And so then now that element has become radon. Okay, and so understand what we've got here. We had radium, which is the parent nucleus. It loses a particle, which is alpha radiation. And then it becomes radon 222, which is the daughter nucleus. Okay, so we had atoms of radon. They lost this alpha particle and became we had atoms of radium. They lost this alpha particle and became radon, right? So we had a large nucleus. It lost a particle, and we have a smaller nucleus left over. Okay? Alpha. This guy's an alpha. Okay. Any questions on that before I go on to the next example? I know that's new. You're going to get an opportunity to practice it. It's okay. All right. So the next type of radiation that we want to be familiar with is called beta radiation. So with beta radiation, it is a negatively charged particle, and it's equivalent to an electron. Okay, and so before we talk too much about that, something should not make sense out of that. All right, so you've got the nucleus of an atom, and beta radiation is like giving off an electron. What's wrong with that idea? Something's not right there. Send me a direct message if you can think of what's not right about an electron being the particle that's given off in beta decay. Let me ask you guys a question. Where are electrons located in the atom? Where are electrons located? Thank you. Thank you for these responses. Thank you. Yeah, electrons aren't in the nucleus. Electrons are outside the nucleus, right? They're orbiting outside the nucleus. And so it kind of shouldn't make sense that an electron is being given off from the nucleus. So the question is, well, where'd that stinking electron come from? So here's the theory, here's the philosophy. Oops. An electron has a negative charge. A proton has a positive charge. If you put a negative charge and a positive charge together, what kind of charge will you have? If you put a negative and a positive charge together, what kind of charge will you have? Thank you. Thank you. Right. A negative charge and a positive charge put together, they will cancel each other out and become neutral. And so I don't know if you guys remember from the first day of the unit, but the idea there was that um, the neutron was just a little bit heavier than the proton. And so part of the philosophy is the proton is added with some small negatively charged particle, not an electron, but like an electron, to give it an overall neutral charge, to give a neutron an overall neutral charge. And so let's say we've got the nucleus of an atom, right? So here we've got 2 protons and 2 neutrons. The idea is that in beta radiation, one of those neutrons splits and emits the negative portion of that neutron, and what you're left with is a proton. And so what happened here is one of the neutrons turned into a proton and gave off a beta particle. One of the neutrons splits, spits out the beta particle, and becomes a proton. Okay, and so as a result of that, the symbol that you see there is a 0 in the upper left, because a proton and a neutron has relatively the same mass. So there's no change to the mass number, but you've got a -1 in the lower left because a neutron has turned into a proton. So you're going to have one more proton than what you started with. And we are going to do an example of that right now. Okay, beta decay. If they tell you you've got a beta decay, that means that the particle that is given up is going to be a beta particle. And so the symbol that we saw there was kind of like this fancy B, right? It's the Greek letter beta. It's uppercase letter B in the Greek alphabet. And in the upper left, there was a 0. In the lower left, there was a -1. That is the beta particle. Okay, so carbon-14 is radioactive, right? We saw from our lesson, our atom builder lesson on Wednesday, that it's unstable, and it gives off this beta particle. How do I know? Because the question will tell me that it's a beta decay, okay? And so then we have to determine, right? So this is the parent. This is the radiation. We have to determine what the daughter nucleus will look like in this beta decay. Okay, so if we started with 14 protons and neutrons, right? So 14 protons and neutrons, and we had 0 change to that, what's going to be the new number of protons and neutrons? What's going to be the new mass number? If we started with 14 and we made no change to that, what's going to be the new mass number? Thank you. Appreciate it. 14. Right? No change. No change means no change. Okay. Now let's look at the number of protons. Okay. So the number of protons we had was 6. And one of the neutrons is going to turn into a proton. So if the number of protons was 6 and a neutron turns into a proton, how many protons are we going to have in the daughter nucleus? Thank you. Right? A neutron turns into a proton. Thank you. Thank you. Thank you. Right? So we had 6 protons, and one of them will turn into a neutron. That's going to leave us with 7 protons. Okay? And if we look at this, this should make sense to us, right? Because mathematically, this is what it says. It says 14 equals 0 plus 14. That's true. 14 equals 0 plus 14. And then it says 6 equals -1 plus 7. That's true too. 6 equals -1 plus 7. All right? And so algebraically, the number of protons and neutrons, the mass number, and the number of protons, the atomic number, all of this equals out in these decay equations. And so now the last thing to do is to figure out what element has 7 protons. And so I would go to the periodic table and find atomic number of 7. Looks like that's going to be nitrogen, right? Right, so our parent nucleus is carbon 14. When it gives off a particle, that particle is really small. And so then the daughter nucleus is nitrogen 14, right? The mass stays the same, but one of the neutrons has turned into a proton. Okay. All right. All right, and so the last type of radiation that we want to be familiar with is gamma radiation. So gamma radiation is not a particle at all. It is high energy radiation with no mass. It's a type of electromagnetic wave. And so basically it's energy being given off. It's not a particle. And it usually accompanies some type of particle, either alpha or beta, being given off. And so what happens there is that you've got, let me make a quick diagram here for you guys. So what happens there is that you've got your parent nucleus. It gives off some sort of radiation, and you're left with a daughter nucleus. But then energy is given off, right, as a result of that. That's gamma radiation. Right, so you get your emitted particle, your daughter nucleus, and gamma radiation given off as a byproduct of breaking that nucleus into smaller parts. And so when you think of like nuclear energy being produced at a nuclear reactor, that is gamma radiation being given off by the splitting of the nuclei. When you think of like a nuclear weapon, like a nuclear bomb, that energy being given off is gamma radiation from the splitting of the nuclei. Right, so gamma radiation usually accompanies another particle, okay? And then you see the symbol here. If you look at the symbol, you can see that the mass number is 0 up at the top left. And the atomic number is 0 down at the lower left, because this is not a particle. We can represent it with a symbol, and that little fancy Y is the Greek symbol gamma, right? So it's, again, from the Greek letter. It's a Greek letter from the Greek alphabet. It's the Greek symbol gamma. But the particle, there's no particle involved there. That's just the energy that's given off. Okay. All right. Are there any questions before we wrap up and I send you guys into the weekend? I've got a couple of, I've got a summary that I'm going to do with you guys here, and then we'll wrap things up. Okay. 3 types of radiation we want to be familiar with: alpha, beta, and gamma. This is the symbol for alpha radiation. The overall mass of an alpha particle is 4 atomic mass units, and the overall charge is +2. So it's made up of 2 protons and 2 neutrons. The mass is 4, and the charge is +2. Beta particle uses this symbol. So it's the Greek symbol beta. 0 at the top because the mass of the particle is basically negligible. -1 at the bottom because a proton comes from a neutron, or a neutron turns into a proton. So the mass is approximately equal to 0. And a beta particle is like an electron. It's not an electron, but it's like an electron. And so it's got a -1 overall charge. Gamma radiation uses the symbol, Greek symbol gamma, and it's got zeros at the top and the bottom because it's not a particle at all. So there's absolutely no mass. And since there's no particle, it has no charge at all. Okay. So for today, the first thing that I think you guys have to finish up is the handout from Tuesday on average atomic mass. And then the second thing that you have to finish up is the guided reading assignment from yesterday. Oops. And then on today's handout, you are going to be given 4 particles that you have to write a decay equation for. And so take note of this, right? It tells you that these 2 are alpha decay, which tells you that the radiation given off is an alpha particle, right? This particle right here. And then you have to determine, you have to write the equation and determine what the daughter nucleus is. And then these 2 are beta decays, which tells you it gives off this particle. And then you're going to have to write the equation and then the resulting daughter nucleus as well. Okay, so that'll be today's assignment. Tomorrow, I am going to show you guys a video on the Manhattan Project. The Manhattan Project is the United States effort to build nuclear weapons during World War II. And if you know your history, you know that that was successful in some ways. And so the video I'm going to show you guys tomorrow is from the video series from the History Channel called Modern Marvels. I think it's pretty well done, and that's why it's one of the only videos I actually show in chemistry. I think it's pretty well done. Helps give you a very historical perspective of why scientists built these nuclear weapons. And then it does give you a scientific perspective as well. There's great video footage of the bombs actually being detonated in action, great video footage of the test bomb being detonated. They interview the actual pilot that dropped the bombs over Japan in World War II. They actually interview some of the scientists and some of the children or grandchildren of the scientists that designed the weapon. And it really presents to us a very important, I think, moral question having to do with designing and using weapons of this type. And so I do want you to watch for that at the end of the video, where they talk about the impact of these types of weapons. And so, like I said, there's a historic as well as a scientific perspective that I want you guys looking out for. And there will be some notes, some guided notes that I'd like you guys to fill in along as you watch the video. Okay. And so that is going to take you into the weekend. On Monday, we do not have classes because we have that day off. And so I will see you next time on Tuesday.